Stress-strain relationship. Let us recap these concepts which you have discussed in mechanics of solids in the earlier semesters. These are essential in the design of machine elements as we will be using them again. So these basically will provide a quantitative measure of the responses of the components subjected to external forces. Okay. Begin with stress. Let us take a simple situation where there is a small link subjected to an axial load, right? So what is the response here? Stimulus is the applied load, response is the resistive force. So how do we quantify here? So the resistive force measured per unit area is what we call as stress. So we assume that there is no stress concentration here far from the point of application of the load, and all fibers of the member are pulled with equal force. We denote it using sigma. Okay, so when we say suffix T, it is actually tensile stress. P is the applied force and A is the cross-sectional area of the member, which is constant. So when the fibers of the part are pulled, or when they tend to elongate due to the applied load, we call it as tensile stress. On the other hand, when the applied force tend to shorten the same fibers, the stresses induced are called compressive stresses. We measure the stress in terms of Newton per millimeter square, or MPa. 1 MPa is equal to Newton per millimeter square. So you can write just MPa or 1 Newton per millimeter square. So this is one response. The other response is the strain, that is deformation. So when we apply this force, the member tends to deform. In this case, we are applying a tensile force, so it will try to elongate. So what is the quantity of deformation? What is the quantity of elongation? So it is strain is measured as a deformation per unit length, that is change in length by original length. Since there is elongation here, elongation of the rod by original length of the rod. Original length here we take usually the gauge length. So it is a unitless physical quantity. Strain doesn't have any units. Okay. So when we pull the same member to a certain limit, that is within the elastic limit, you know this, the stress induced is directly proportional to the strain, and as a consequence we have Hooke's law, right? The proportionality is replaced by a constant known as Young's modulus, or modulus of elasticity. Physically it is a measure of the stiffness of the atomic bonds. So the unit is usually GPa. So we always use this standard units, GPa for elastic modulus and MPa for stress. Strain doesn't have any units. So now let us recast the strain equation applying Hooke's law. So delta is equal to PL by AE. This is the expression for elongation. And while employing these stress-strain equations, we must be careful because these are derived under the set of assumptions, right? So they are the material assumption. We assume that the material is homogeneous and the load is gradually applied, static load. The line of action of force P passes through the geometric axis of the cross section. So there is no eccentricity. And the cross section is of course uniform. Only when these assumptions are satisfied to the selected part, we can apply these formulas. Yes, there is no stress concentration. See, you cannot measure the stress close to the point of application of the load. So this is where Saint-Venant's principle becomes relevant. Okay, so we have to apply Saint-Venant's principle and measure the stress uh, 2 or 3 times the characteristic length of there is smaller characteristic length of the specimen. That is, from the point of application of the load, you take 2 or 3 times the smallest characteristic length of the specimen. If it is a circular one, 2 or 3 times the diameter. Far from the point of application of the load, we have to measure the stress, because usually you will have no stress concentration at that point. Shear stress, this is another type of stress. So there is a a plate assembly fastened by a rivet. When we apply forces as shown in the figure, the rivet will shear into 2 parts, right? So if you take the cross section of the rivet, the forces act parallel to the cross section area of the rivet. That is, the component tends to slide on the adjacent plane with respect to each other. So the resistive force is known as, in this case, direct shear stress. Okay, so the average shear stress is given by tau is equal to tangential force P divided by the cross-sectional area over which the tangential force acts. The unit here again, it is Newton per millimeter square or megapascals. Accordingly, we have shear strain also. So we have a rectangular element here. Okay. So now when we apply a shear force, there is a force acting along the plane of the component as shown in figure A. The element distorts, right, from its original right angle. So the change in angle, the distortion is measured by in terms of change in angle. So this is what quantifies the shear strain, the change in the right angle of the shear element. So within the elastic limit, again Hooke's law holds, that is tau is proportional to gamma. The constant of proportionality is G, which we call it as shear modulus or modulus of rigidity. Okay, and again G, modulus of rigidity, is written in GPa. Okay, of course you can express that in MPa also, but the convention is to use GPa. What is the relation between the elastic constants? Like there is one more elastic constant, bulk modulus, we have discussed in earlier classes, which is the ratio of the applied hydrostatic pressure to the change in volume. That is K is equal to P divided by delta V by V. So the relationship between these three elastic constants are frequently used in solving design problems. Okay, so you must remember them. E is equal to 3 times of bulk modulus into 1 minus 2 mu, that is Poisson's ratio, and E is equal to 2G into 1 plus mu. Now let's look at a case where we have a different type of external force here. Rather than the axial force, we have the bending moment. You take a member, apply the bending moment on its either ends. So its cross section is rectangular. Okay, so a straight beam here is subjected to bending moment M suffix B. So if you look at the distribution of the stresses, so when you try to bend in the manner shown in figure, the top layers of the beam will be subjected to compression, whereas the bottom layers of the beam are subjected to elongation, that is tension. And there is a transition, right, from tension to compression. The plane, the transition plane, is what we call as neutral axis, where the fibers lying on the neutral axis remain undeformed, right? So cracks, of course, will tend to appear on the outer surface of the beam because of the tensile forces, whereas the folds will appear on the top surface due to compression. Okay. So how to evaluate these stresses? See, remember, in case of bending, we have normal stress, and we are dealing with only pure bending. In case of pure bending, we ignore the shear stress, because in comparison to the magnitude of the normal stress and its characteristic dimensions, the, the shear stresses are safe to ignore. So the bending stress, we are not going to derive it. Let us just take the formula. Sigma b is equal to mby by I, where is sigma b is the bending stress in MPa, mb is the applied bending moment, and I is the moment of inertia of the cross section about the neutral axis. So clearly, uh, when y is equal to depth by 2, that is at the outermost fiber, the bending stress is maximum. And the distribution of stress, normal stress in the cross section of the beam is linear, which we know it, and again from that above formula. So again, this bending equation is based on this following assumption, and it holds good only under this situation. The beam must be straight with uniform cross section, and the forces acting on the beam lie in a plane perpendicular to the axis of the beam. Okay, very important. And material is homogeneous, isotropic, and obeys the Hooke's law. Plane cross sections remain plane after bending, so there is no out of plane bending. Okay, so another type of load is torsional load or twisting moment. Okay, so here we have a small cylindrical rod whose one end is fixed. On the other end we are applying a twisting moment denoted by mt. So due to mt we have torsional shear stresses, and its distribution is shown in the figure, right, whose variation is linear, with zero at the center of the shaft and maximum on the outermost fiber of the shaft. The torsional shear stress equation is given by mtr by j, where tau is shear stress in MPa, and mt is the applied torque in Newton millimeter, r is the radial distance of the fiber from the axis of rotation, and j is the polar moment of inertia. So please be consistent with the units. For length you use only millimeter, because we use MPa and all. Okay, so the distribution, yes, it was shown, it was linear variation. Angle of twist, yes, mtl by jg, this is known to you. And these equations are again valid only under these assumptions. The shaft must be straight with a circular cross section, and we are not dealing with non-circular shafts. Okay, only circular shafts. There is no out of plane twisting, and material, yes, must be homogeneous, isotropic, and must obey Hooke's law. Polar moment of inertia. These formulas, of course, you must remember for different geometries. Okay, so for a circular shaft of diameter d, it is pi d power 4 by 32, and for hollow circular shaft it is given. And power transmitted by the shaft is power is equal to 2 pi nmt by 16 to 10 raised to 6, where n is the speed of rotation in rpm. So please remember these basic formulas, which we will be using often in the design of machine elements problems. Okay, thank you.